Stochastic reflection problem of convex.
Good afternoon, everyone. First, I would like to thank the organizers to give me the opportunity to give a talk here. My talk is about Beauty functions in a Gelfand triple and the stochastic reflection problem on a convex set. This is a joint work with Professor Rockner and Rongchan. Now we consider this stochastic differential inclusion in the Hilbert space. Here, A is a positively definite self-adjoint operator, and gamma is a closed convex set. And this n gamma is defined as here is a normal core to the gamma at x, and Wt is the cylindrical Wiener process here. So we can see that if gamma is regular convex set like here, then this n gamma is just in this directions. It's like in this directions. It's like here, and if this gamma is at some point x is singular, then this n gamma is this set is a normal core at this x. So this n gamma is the subdifferential of this E gamma defined as here. This E gamma is a potential function here. So we can see that this term just make the process when the process hits a boundary, and it will reflect at the boundary here. So this term pushes the process always stay in this gamma here. So we'll call it the reflected problem here. And this problem in infinite dimensions has first been considered by Violat and Padu. For gamma is a special kind of convex set, and they get the existence and the uniqueness of this problem. For gamma is a special kind of convex set. And recently, Babu and Prato also consider this problem. For gamma is a regular convex set, and they get the precise information of the corresponding Kolmogorov operators of this problem. But they cannot get the probabilistic strong solutions of this problem. And the main result of this talk is that we can get the probabilistic strong solutions of this problem here. And to solve this problem, we introduce the Beauty functions in a Gelfand triple here. Now first we recall Beauty functions in finite dimensions. A function u is called a Beauty function on Rn if and only if one of the following is satisfied. First says that there exists a real finite Mayer mu j such that this equation is satisfied. This says that the weak derivatives of u exist as a finite Mayer mu j here. And the second says that this Vu defined as here is finite. This means the divergence of phi, and phi is the test vector field here. And the equivalence of these two definitions can be proved by using Riesz repetition theorem. And now we want to give the definition of Beauty functions in infinite dimensions. We know that here we choose this reference Mayer as the Lebesgue Mayer, but we know that in infinite dimensions there's no Lebesgue Mayer. So now we take the Gaussian Mayer as the reference Mayer. Below mu will denote the Gaussian Mayer in H with mean zero and covariance operator Q defined as here. And here this a to the power minus 1 is of trace class. So this Gaussian Mayer in a Hilbert space. And now we first give a definition of directional Beauty functions on H if and only if one of the following is satisfied. First says that there exists a real finite Mayer mu L such that this equation is satisfied. Here D means the Fisher derivatives of V here, and mu is a Gaussian Mayer as we define as here. And we can see that it means that the weak derivatives along this direction L of u exists as a finite Mayer mu L here. And the second says that this VLU defined as here is finite. This will also change the reference Mayer to the Gaussian Mayer here. But the equivalence of these two definitions cannot be proved by using representation theorem, since we know in infinite dimensions there is no lack of local compactness here. But Fukushima proves a version of representation theorem by using deletion form theory, so we can use his result to overcome this difficulty. And also, if we just take the intersection function of these directional Biot functions as a direct definition of Biot functions in infinite dimensions, this does not give rise to vector-valued measures representing their total vector derivatives or gradients. There are some definitions of Biot functions in infinite dimensions. First was given by Fukushima. He defined the Biot functions in abstract Wiener spaces, and also later he and Kino extended these definitions also in abstract Wiener spaces. And Ambrosio de Prato and Palara also give a definition of Biot functions in the Hilbert space. If this V rho defined as here is finite, this D star means the weak derivatives of means the adjoint operator of the Fisher derivatives of here, and we let this H norm of G is smaller than 1 here, and this is a definition of the Biot functions in the Hilbert space. And now we want to extend this definition in a Gelfand triple. Now let H1 and H and H1 star be a Gelfand triple. Here, this Gelfand triple means that this H1 is a subset this H continuously and densely, and now we this H is Hilbert space, and we identify H with its dual H star. Then we have this subset H1 star. So we call this H1, H and H1 star be a Gelfand triple. And now we define this Biot functions in a Gelfand triple. If this V rho defined as here is finite, here we just change this test vector field G from this H to this H1 space, because the idea to introduce this Biot functions in Gelfand triple is very natural. Since Biot function means that the weak derivatives exist as a vector-valued measure, but this vector-valued measure may not convergence in H space. It may convergence in this H1 star space. So we let this test vector field live in this H1 space, and this give this definition of Biot functions in a Gelfand triple. And we have an example that is a Biot functions in a Gelfand triple, but not a Biot functions in Hilbert space. And now we have this theorem. This theorem is a characterization of Biot functions in a Gelfand triple. If rho is a Biot functions in a Gelfand triple, then there exists a finite measure D rho and a map sigma rho such that for any test vector fields G, this equation is satisfied. This means that the weak derivatives of this rho exist as this vector-valued measures here. And the second says, conversely, if this equation is satisfied, then this rho is a Biot functions in a Gelfand triple here. So this theorem is just an extension of the two definitions of Biot functions in finite dimensions. And now we want to consider the reflected problem on a regular convex set. We consider the situation when rho is equals to the indicator function I gamma. Here gamma is a regular convex set. Can be written like here. G is a regular function here, and we know that this unit ball in a Hilbert space satisfies this condition, and we can prove that this I gamma is a Biot function in Hilbert space. And now we want to construct the reflected OU process on this gamma. But we know that sometimes to construct the strong Markov process in infinite dimensions is difficult. But the quasi-regular deletion form provide a useful means. So we now consider this deletion form. Here, du means the Fourier derivatives here, and rho is also the indicator function I gamma, and mu is a Gaussian measure as we defined before. And we can prove that this is a quasi-regular local deletion form. So by Ma and Rockler's book, there exists a diffusion process M rho associated with this deletion form, and this process is.
What is the mu? What is the mu? What is the measure now?
Gaussian layer, as we defined before. And this process will be called the reflected OU process. And then we can see that under this PZ, there exists a cylindrical inner process WZ, such that the sample path of this process satisfies this equation here. Here we can here this sigma rho is just the internal normal to this gamma, and this LS is a positive continuous active function corresponding this surface measure here. So this LS is increasing, continuous increasing process, and it increases only when the process hits a boundary. So we can see that this term represents the reflection term here, and this theorem can be so we call this is this process is reflected OU process here. This theorem can be proved by using Fukushima decomposition. So this term is martingale additive functional, and this two term is zero energy additive functional here. And now we can consider this 1.1 as I mentioned before. First, we give the definition of this problem. It's a pair of continuous adapted process XT and LT. It's a probabilistic strong solution of this problem 1.1 if it satisfies XT is always in this gamma. Since it's a reflected problem, it's always in this gamma. And L is an increasing process, and it only increases when the process hits a boundary. And it also satisfies this equation here. So this term represents the reflection term. This definition is an extension of such kind of problem in finite dimensions. And from this definition, we see that this theorem gives weak existence of weak solutions of this problem. So we can also prove this the pathwise uniqueness of this problem. Then by Yamada-Watanabe theorem, we can get the existence and uniqueness of the probabilistic strong solutions of this problem. This is the main result of this talk. And also we can consider this special case when H is the L2 space and rho is this IK alpha. Here K and A is minus Laplacian with delicate boundary conditions on 0, 1. Here this K alpha is this set for alpha bigger than 0. This is a convex set but with empty interval here. And we can find a suitable H1 such that this IK alpha is a Buell function in this Gelfand triple. But this is not a Buell function in Hilbert space. So that's why we introduce the Buell function in a Gelfand triple. And now I want to mention some extensions. We can extend all this result to non-symmetric deletion forms obtained by a first order of the above deletion form. Before we just consider the symmetric deletion form, here we consider the non-symmetric deletion form. So we can plus a nonlinear term bx here. But this non-symmetric deletion form should satisfy the circular condition. So this b should be bounded here. And also, if this B satisfies more conditions, we can also get the existence and uniqueness of this problem here. And also, since the definition of Beer functions for the to have the integration by parts formula in infinite insufficient many directions is essential to this definition of Beer functions. So we can replacing the reference Mayer Gaussian Mayer with a differentiable Mayer nu. And in particular, if we just take this nu is P phi 2 quantum field, we can get a martingale solution of this stochastic quantization problem with reflection in infinite volume. Here, this Px means a polynomial term, but it's defined by the weak ordering here. And this term also represents the reflection term here. And we can also just take this nu is has a density with a Gaussian Mayer. This mu is a Gaussian Mayer defined as before. And we can also get the existence and the uniqueness of the probabilistic strong solutions to this problem, just plus this nonlinear term here. And this is also the reflection term here. And that's all. Thank you.
You have a Gaussian measure on H, and what is the covariance operator of the Gaussian measure? Which scalar product from which Hilbert space? Or covariance of the Gaussian measure?
Defined by the A.
H1?
No. Defined by the A to the power minus.
Okay.
Yeah.
Okay. And how you prove closability of the pre-Dirichlet form?
Because this set is this set defined as here is closed convex set, so we can prove it satisfies the Hamada condition. So it's closable Dirichlet form.
Aber Hamza condition.
Yeah.
So you don't have integration by parts.
No.
Okay.
But this indicator function is BV indeed, because it is plus infinite outside convex K.
You mean this?
I gamma.
Yes. It's a Beer function.
But it is plus infinite outside K. I don't know.
I think,
No. It's
I
not
think it's
plus
PV in this
infinite.
Gelfand triple. Maybe you need some.
No, it's not plus infinite. It's
No?
It's in equals 1 in the gamma and then equals 0 outside gamma. It's not.
No, this is characteristic. This is indicator function is plus infinite outside. This is
It's a question of definition. This is 1 on gamma and 0 outside.
Yes. Yeah.
You restrict the process by
but the
putting-
subdifferential in this case is not normal cone, if you take so. No? Perhaps. Now, in general, if you take indicator function of to be normal cone, we should take plus infinite outside.
If you want to have this as a subgradient,
Yeah, if you want to write in this form, that's okay. Perhaps. This is.
Why you need this Gelfand triple structure? Where
You mean here?
you need some special properties. H1 is just continuously and densely embedded, or some must it be Hilbert-Schmidt, or just.
Just actually, we also need this H1 is also a Hilbert space. Is also a Hilbert space. Yeah. We need this because we can have.
So you could also choose H1 equal to H.
Yes.
Yeah.
In the example you showed about, you said you can construct Hilbert space H1 oh, here.
Yeah.
So what sort of H1 is this Hilbert space?
The first order Sobolev space. Something like this.
An example is this should be H1 Sobolev space and the one space. Other questions?
Yeah, I mean, this, of course, coming back to what you were, I mean, is there a formulation where you could use the maximum monotone operators instead to construct a strong solution?
This means that if you use effects as a normal cone, it's maximal monotone in Hilbert space, in this case. Now, the problem is about subdifferential.
Yeah.
Okay, perhaps. Other questions? Yeah, me too.
Maybe you should give the references.
Yes, I just don't put it here. I didn't just put it here.
But maybe you can say where this.
The two major references. First is about the Bab and Apparato, and the other guy's paper about the chromograph operators of this problem. And another one is for the Fukushima's paper, the Build functions in abstract Wiener spaces. That paper.
And these results are published in Annals of Probability.
Yeah, yes.
More questions? Okay, thank you.